Hello and welcome to this presentation. My name is Khazar Ahmadi and I'm excited to share our findings on feasibility of mesoscale VASO recordings in human hippocampus. I have no financial interests with respect to this project. The human hippocampus is a critical region for memory and navigation. It consists of subiculum, four cornu-aminous regions, dentate gyrus, and the stratum radiatum lacunosum molecular. The hippocampus is generally considered a challenging target for laminar fMRI. This is partially due to signal dropout associated with its anatomical location. Moreover, it has a different laminar structure and macrovasculature than neocortex, and this poses additional hurdles for the analysis of laminar resolution data. Recently, a few studies have shown feasibility of laminar recordings in the hippocampus using gradient echo EPI sequence with bold contrast. However, the specificity of bold signal is compromised by draining veins bias. This is even more crucial in the hippocampus as the blood drains from both inner and the outer surfaces. The aim of this study was to mitigate the contribution of macrovasculature by optimizing VASO to capture hippocampal activity. Nonetheless, there are a few methodological constraints regarding the application of VASO in the hippocampus. First, the relatively short arterial arrival time can cause inflow effects. Second, large field of view and deep eddy currents in deep brain structures can lead to EPI phase errors. And finally, the distance of RF receivers can contribute to low TSNR that is typically observed in the hippocampus. We set out to develop a VASO protocol tailored to hippocampus by scanning 13 participants over 19 sessions using 370 Siemens scanners with PTX system based on the scanner availability. We further disconnected third-order shim to reduce gradient resonance artifacts. And if you are interested to learn more about this topic, check the abstract 0287. We started with a 3D GE-EPI sequence that has been used in one of my previous studies and a study by Pfaffenroth and colleagues with an isotropic voxel size of 0.8 mm and bilateral hippocampus coverage. To boost the TSNR, we opted for unilateral hippocampus coverage in sagittal orientation, and to do so, we reduced field of view, grappa, and base resolution and adjusted bandwidths and partial Fourier. Based on this acquisition setup, we then implemented a 3D slab selective VASO with concomitant acquisition of VASO and bold images and effective temporal resolution of 6 seconds with volume TR of 2.5 seconds and blood nulling inversion time of approximately 1500 milliseconds. As can be seen here, the API quality can be improved by disconnecting third-order shim, bandwidth adjustments, and readout in Z direction. The inflow effects are primarily visible in large Pial vessels, and the inflow modulations in hippocampus are similar to neocortical regions. We further compared STX and PTX head coils and found that for both bold and VASO images, the TSNR in the hippocampus was slightly higher for the STX compared to PTX coils. Many researchers asked the question, should I scan with STX or PTX coils? To find out more, see the abstract 2333. And since we had access to 3 Siemens scanners, 2 identical Terra systems, and 1 classic 70 plus, we decided to examine TSNR in the hippocampus for VASO images and found comparable values, suggesting the stability of the sequence across scanners. And finally, the optimized sequence was validated with an autobiographical memory paradigm in which specific keywords were presented to subjects and they were instructed to think about a related memory as vividly as they could. Following a short break, they were asked to perform a simple mathematical equation, find the answer, and keep adding 3 to answer until the next pause trial. VASO-optimized Nordic denoising was applied to the data. Distortion and motion correction were conducted using ANTs. The VASO data were further corrected for bold contamination using Laney. and the alignment between structural and functional data was performed using ANTS or AFNI tools. And finally, the hippocampus was segmented into its subregions, and the surfaces were delineated using HipUnfold. I hope you agree with me here that there is a decent alignment between VASO and the underlying anatomical image, and the TSNR for all task-based VASO runs are fairly high. Similarly, the bold data show a good co-registration with the underlying T1 image, and unsurprisingly, the TSNR of bold data is significantly higher than the VASO. We then performed GLM analysis and included motion estimates as well as white matter and CSF signal fluctuations as nuisance regressors in our model. As depicted here in two representative subjects, the activation patterns for bold and VASO images were quite similar. Further, predominant math-related activation was observed in parietal regions, whereas memory retrieval was associated with frontal and hippocampal activation. To do group-level analysis, we created a study-specific T1 template shown here in the middle panel. The bottom panel displays individual T1 images warped to template space. As can be seen here, there is a nearly perfect alignment in the hippocampus, but less so in some neocortical regions, including parietal cortex. Following group-level analysis, again, a similar activation pattern was observed between bold and VASO, although bold data showed a slightly higher sensitivity. I would cautiously say here that memory retrieval at group level evokes hippocampal activity based on this few significant surviving clusters. And likewise, there seems to be mass-related activation in parietal regions at group level. To extract laminar profiles, the inner and outer surface of the hippocampus were divided into 20 equidistant bins, and we further extended the sampling by another 10 bins from the inner surface to cover SRLM in cerebellum, CA1, and CA2. I'd like to highlight here that the draining vein effects should be more pronounced in the inner surface for cerebellum and CA1 and in the outer surface for CA2 and CA3. As for the sources of input, the inner surface receives direct input from the entorhinal cortex, while the outer surface predominantly receives input from the trisynaptic pathway. Prior to doing the same GLM analysis on depth-dependent signal, the layer time course of bold and VASO were Z-transformed using mean and standard deviation of volumes corresponding to math trials. In cerebellum and CA1, the bold signal shows a peak at the border of SRLM and inner surface, and this is in line with the expected vasculature effect in the hippocampus. Interestingly, the VASO profile show opposite pattern. In CA2, we see an increasing pattern at the outer depths for bold, and again, this is in agreement with the expected draining vein effects, whereas we see a decreasing pattern for VASO profiles. In CAC, however, the laminar profiles of both bold and VASO are comparable. Given the involvement of CA3 in pattern completion, in which partial cues activate a conjunctive representation of an entire experience or episode, this finding could potentially demonstrate the contribution of trisynaptic pathway at mesoscale to memory versus mass condition. Furthermore, our bold profiles are largely in line with this recently published study. To summarize, I hope I could convince you that VASO can be successfully implemented in the hippocampus. The macrovasculature contribution can be mitigated in the hippocampus using VASO, and our findings provide a foundation for future applications of VASO to better understand hippocampal microcircuitry. Finally, I'd like to mention that there is a parallel effort to use VASO on advanced hardware of next generation 7T scanners, and for further details, please check the abstract 8017. With that, I'd like to thank my co-authors, other scientists providing technical and institutional support, and thank you. I'd be happy to take any questions.